All right, so we talked about some hypothesis testing in class today, and I didn't like how the explanation went, so I thought I'd give it another shot and do it a little better. This problem right here is dedicated to Liko, who likes to fish, and it's very, very similar to the wording that was used on exam B with some different numbers and circumstances, but the rest of the problem uses the same words. So first of all, I'll let you read it and kind of determine what the key values are and then what we're trying to accomplish. So hopefully you've read through that. If not, you can pause the video. We have a couple pieces of key information. We know there's 35 trout in Liko's sample. So this is Liko's sample. I don't know why it's pink. Sorry, Liko. Liko's sample has a sample mean of 19.2 inches, and it has a total of 35 trout. That's a good day fishing. And then the sample standard deviation is 1.25 inches, or at least the trout were determined to have a length of 19.2 inches. So if this is a good sample of trout in Winchester Lake, does it provide significant evidence that the true mean length of the trout is longer than 18 inches? So what we're trying to say here is this good evidence that our trout are, on average, in the lake in the population, longer than 18 inches? Typically, if you see this kind of question in an LCSC Math 123 course or even a Math 153 course, they're going to ask you to write an alternate and null hypothesis, symbolically and using words. And then they'll ask you to calculate the test statistic. Something that is important here is I wrote down the sample standard deviation as 1.25, but if you look at the next question on this problem, I'll copy it right out of the test. It asks you to calculate the value for the test statistic z. So if we, in a Math 153 setting, you actually have tools to talk through what to do when you only have a sample standard deviation. But here, a z-score, keeping in mind, is always going to be this fancy equation, where again the x bar here is your sample mean. This is the estimated population mean, sometimes written as mu naught. This is your population standard deviation, and this is the total n in your sample. So if we're going to use a z-score, and the test is asking us for a z-score, we need to assume that this is a population standard deviation. And in some cases that may be true, and some it may not. For the sake of the Math 123 course, unless you see the word sample standard deviation, it is likely that you're assuming that this is a population standard deviation. We can use a z-score. If you care, the way that we would do this if this was actually a sample standard deviation is we'd use a different test. We'd use something called a t-test statistic, which is pretty dang similar to the z-test statistic, but then we are using the sample standard deviation, and the t distribution looks a little different than the normal distribution. But that doesn't matter for this course. We're going to calculate our z statistic here in just a moment. But first, let's formulate our null and alternate hypotheses. When we're talking about null hypothesis, as I wrote, this is going to be that nothing changed, and the alternate hypothesis is that something is different than we originally are assuming. The way I like to write this down is I usually write the alternate hypothesis first. In this case, the alternate hypothesis is given to us. Is there significant evidence that the true mean length of trout is longer than 18 inches? So that's our alternate hypothesis. The population or true mean length of the trout is longer than 18 inches. That's it. If we want to write that symbolically, we might write it as H sub A for alternate hypothesis is that the true mean is greater than 18 inches. Typically, it doesn't have to be this way, but for almost all of the problems that you might see in a 123 or 153 course, your alternate hypothesis is going to have an inequality, such as greater than, less than, or not equal to. Those are inequalities. Whereas your null hypothesis for this kind of hypothesis testing of a mean is going to have an equal sign. So the null hypothesis is simply that this is not true. And mathematically, that's equivalent to saying that the population mean length of the trout is 18 inches. Symbolically, that would look like H naught is how we write that. That little zero thing is a naught if you're British, like crosses and noughts, the tic-tac-toe game. And we're asking if H naught, null hypothesis, is that the population mean is 18 inches, not this, which is mathematically equivalent to looking at what happens before 18 inches. So this is kind of our setup normally for these hypothesis testing of means. And now we're going to use a z-test statistic to convert this situation to a normal distribution that we can easily do math on. The normal distribution has a mean of 0 and a standard deviation of 1. And that is what this z-score does, is it finds the z or standard deviation if this was on a normal distribution, which allows us to make calculations and conclusions about probabilities. We can also do this with the normal CDF function on our calculators, but this is the method we're using right now. So let's go ahead and calculate that. It looks like this. Boom! With a little bit of color coding to make it clear where the values came from, I'll just plug that in my calculator. Remember that when you have a fraction written like this implies that the top is grouped and the bottom is grouped. If you try to type it in a calculator without those groupings, you won't get what you expect. So make sure to make those groupings. Either way, when you do this, you get a z-score of approximately 5.678. That's our new z value. What this means is that if we were to convert this sample to a situation where this is the proposed population mean, this particular sample would be approximately 5.678 standard deviations to the right of the normal distribution mean of 0. So that 5.67 is going to be over here. There's 1 standard deviation, 2 standard deviations, 3 we're already getting pretty small, 4 is really small, and 5 is teeny, teeny, tiny. So the area we're shading is to the right or the left. This gives us our hint. This is a right-tailed test. We're looking for means greater than 18. So we would be shading this tiny, tiny area to the right of 5.678. Standard deviations away from the mean of 0 in the normal distribution. There is a function on calculators we can use to calculate this. For some, it's norm CDF, and there's different formats of this. The long and short of it is that our lower bound, since we're doing a right-tailed test, is right here, that 5.678, and the upper bound is all the way to the right as far as it goes. That's infinity, and if you can't type infinity on your calculator, just put in a really big number. 100,000 is probably sufficient. I like to add some extra zeros because it makes me feel more safe. I don't know. And just we're labeling this. This is the lower bound. This is the upper bound. In some calculators, you will also be required to enter the population mean and standard deviation. And if we've converted to the normal distribution, which is what we did when we got a z-test statistic, we are going to have a mean of 0 and a standard deviation of 1. If you need to type that in, for many calculators, you don't actually need to type that. It will assume those values if you don't type those in. Now, as a quick side note here, I did round my z-test statistic here, and on paper that's probably fine. If you do it in a calculator, you may end up with a different result that is enough different that it might be impacting your response and your conclusions. So I don't recommend rounding in your calculator. If you have a calculator that can type like this one and can get precise values, that's great. If you need to do it with parentheses, it would look like this. Because keeping in mind, when you have a fraction bar like this one, it implies that the top and bottom are grouped. And if we don't type those into our calculator, then that calculator may not also understand that those need to be grouped. Either way, we get the same z-test score, and I'm going to use this exact value in my calculation for the norm CDF. For most calculators, if you want to use the value you just had, you can hit a plus or minus or divide, and you'll get this thing called ANS, or answer. There's also an answer button on these calculators. TIs have it down here next to the minus. And when you put in ANS, it will give you the exact value of the last thing you typed in. For this particular calculator, the norm CDF is calculated like this by typing it in. Other calculators may ask you what the upper and lower bounds are. For this one, the lower bound is going to be right here, our 5.678, our z-test statistic, and as a right-tailed test, we're going to the right. So we'll go ahead and type in answer there. Is our left bound, and our right bound is a very large number. And this calculator, we can type infinity. If you can't, you can just use a very large number. It will work fine. And this assumes, as we said, the mean of 0 and standard deviation of 1, and we'll get our test statistic. -9 indicates that this has 9 divisions of 10 to get the number we're actually looking for. And one way I like to think of that is you could write this as 6.77 times 10 to the -9. It's the same thing. A lot of people will write the original number and then move the decimal 9 places to the left, and this gives you the actual value. In any case that you do this in, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now we need that many zeros to fill in. There we go. And then 6, 7 would be what happens next. In any case, this is a very small number. It's certainly less than the significant value that we use in our courses of p less than 0.05. So given this result, our p is less than 0.05, we have evidence in favor of our alternate hypothesis. And our conclusion, because p is less than 0.05, is exactly this. We don't need to think about what our conclusion is. It is that we have statistical evidence. P is this thing, this very small number, that is in favor of the population mean length of trout is longer than 18 inches in Winchester Lake. If our p was greater than 0.05 for this course, then we would accept our null hypothesis. The mean length of the trout is actually 18 inches or possibly less. And this will always work this way for most of the hypothesis tests. It is easy to remember that our significant value of 0.05 is where we will start to accept the alternate hypothesis, and our conclusion is either this, if we accept the alternate hypothesis, or this, and we don't have to think about what to write. One more little tip here. The p-value, it seems like this is really small, so it's like really, really strong evidence towards. And I caution using these words because this is not stronger evidence. It is just evidence in favor of this and does not necessarily mean that this is more likely. The technical definition is, with this sample, if the true average length of all trout in Winchester Lake were actually 18 inches, the p-value could be sort of looked at as the probability of catching this sample of 35 trout with a mean length of 19.2 inches or longer just by random chance. We're saying that's probably not random chance based on this p-value, meaning this hypothesis is what we would accept, and there's statistical evidence in favor of that. Okay, enough on that. I do want to talk about an alternate way of calculating this that we did briefly talk about in class. This is not something that is necessary, but for those of you who want to use this alternate method, I wanted to make sure that it was clearly explained. One thing you can do to skip converting our sample into a normal distribution shape, we can actually use the distribution of our actual sample, 19.2 inches, to infinity as a right-tailed test. If we change the mean to the hypothesis mean, and the standard deviation to what we call the standard error, sometimes notated like this. In any case, we will assume the standard deviation for the population 1.25 divided by the square root of the number of samples as our standard deviation. And if you calculate this, just like this, I've typed it in the calculator to save time, you see that it is precisely the same result. Oops, you can't see that screen. I hope earlier the calculator was on the screen too. That would be very sad if it was not. In any case, either of these methods are appropriate and will result in the same answer. I just wanted to clarify that this was what was trying to be done during class today. Hopefully that's helpful.